We can start off with an introduction. So on July 4th, 2012, the Higgs boson was discovered, and that completed the standard model of particle physics. So you can see on the top right here, I've put the full standard model with the fermions in the left 3 columns and the bosons, including the Higgs, in the right 2 columns. So this is great, and that means that we can make predictions using the standard model and predict all the results we've observed so far. But there are still many unexplained questions that the standard model just doesn't address. Something relevant to this talk would be the baryon asymmetry problem, but there are various other problems that the standard model just doesn't address right now. So one particular way to address these questions is to study the properties of the Higgs. And if you observe any deviations from the standard model prediction, that would point to new physics and maybe shed a light on resolving one or more of these unexplained questions. So for this talk, what we want to do is we want to look at the anomalous couplings of the Higgs to gauge bosons, because the current measurements are all consistent with the standard model, but the uncertainty on those measurements is still large enough that there could be anomalous couplings hiding in the uncertainties. So we want to make really good measurements there and see if there's any anomalous couplings. So since we're going to be looking at the Higgs couplings, we should first talk about the Higgs, its production and its decay. So starting with production, there are 4 main Higgs production modes that I've shown the Feynman diagrams for here on the top right. So the largest cross-section is the gluon-gluon fusion, that's just shown in the top left here. And this is the only loop-induced process. So the others are all going to be tree-induced or tree-level processes. So the gluon-gluon fusion has the highest cross-section, as I have in this table on the bottom left, followed by vector boson fusion, where 2 vector bosons come together and produce a Higgs. And that's associated with 2 quarks shown in this Feynman diagram that typically end up far forward in the detector. So that's a signal that we're going to look at later, that signature. There's also the associated production shown in the bottom left, where a W or a Z is produced and it radiates away a Higgs. And lastly, there's the TTH production, where the Higgs is coupling to 2 top quarks. In this case, this is actually not a Higgs coupling to gauge bosons, but Higgs coupling to 2 fermions. And so that's included in a different analysis, and it's studied independently since the vertex is different. Then moving to the decay side. So the Higgs was discovered in the ZZ and diphoton channels. And since then, since 2012, it's been observed also in the di-tau and the BB bar channels. So we've observed the Higgs decaying to all these different channels. And for this analysis, we use the di-tau channel. And the reason is it provides a really good middle ground between the branching fraction and the cleanliness of the signal. So if you look at the bottom right, I've got the branching fractions for some different channels. You'll see that BB bar has the highest branching ratio by far. The issue there is that this decay shows up as 2 jets in the detector, and it gets swamped by the multi-jet background, which makes this end up being a difficult analysis in practice. So that's a high branching ratio, but not a very clean signal. On the other hand, there's the di-muon channel, which is very clean, just identifying the 2 muons coming from the Higgs. But as you can see, the branching ratio is very small. So you can see the di-tau channel is in between these 2 channels in terms of branching ratio. And also, it's a cleaner signal with the main background just coming from the Drell-Yan production of 2 taus. And so, as I said, there's the production and the decay side. For this analysis, we only focus on measuring anomalous couplings in the production side. And there's a different analysis that looks at anomalous couplings on the decay side. So generally discussing these anomalous couplings, I've got the general scattering amplitude here for a spin 0 Higgs coupling to two spin 1 bosons. And it's separated into these three terms that I've highlighted in blue, green, and red. And these terms, they correspond to different physical processes. And then you can see they've all got different coupling constants in front of them. These coupling constants are going to vary depending on the Higgs production mechanism. So I'll discuss those later. But to start, we can just discuss these three highlighted terms. So first, we've got the CP even tree level couplings. This is shown in blue. Then in green, we've got CP even loop level couplings. And in red, this is going to be all the CP odd couplings. So any CP violation that's observed will be in this third term. So we can move on to discuss first the Hvv vertex. This relates to vector boson fusion and associated production. And I've got the Feynman diagrams here with the specific vertex we're looking at highlighted in this blue circle. So we can start by looking at the CP even tree level term, this first blue term. It's got two different coupling constants. First, the A1 constant, which is the pure standard model coupling constant. So in the case that there's no beyond the standard model physics here, the A1 term will be non-zero and all other coupling constants will be 0. And then there's also this kappa over lambda term. Sorry, my cat is attacking me right now. Okay, there's this kappa over lambda term that it scales the CP even contributions from heavy resonances that might not have been observed yet. So it allows new physics to affect this tree level CP even coupling. And just to describe this term a little bit more, the lambda is the cutoff scale at which the new physics would occur. And just to simplify things, we say that the lambda WW and lambda ZZ terms are equal to each other, and we just call those lambda 1. And then there's also a specific lambda term for the Z gamma coupling. Then we can look at the green term, and the coupling constant scaling there is the A2 constant. So this will scale CP conserving loop couplings, since this is a CP even vertex as well. And then, as I mentioned, the third term scales the CP violation. So this A3 coupling constant, that measures the amount of, or that scales the CP odd coupling term. So that's the interpretation for the HVV vertex. And then we can look at the HGG vertex, which relates to gluon-gluon fusion. And so in this case, I've got this big circle on the Feynman diagram showing that we're looking at this loop. And since this is a loop-induced process, this first blue term in the general scattering amplitude is 0, because that is the tree level term. So for the HGG vertex, we've only got the A2 and the A3 terms, which I've added the superscript GGH just to keep them separate from the HVV A2 and A3. So in this case, we've got this loop, and when we write our amplitude in this way, this makes no assumptions about the content of the loop. So there could be new physics present in this loop, or it could be purely standard model physics. It doesn't matter. And then the interpretation is that this A2 term, this is the pure standard model coupling. So this is the one that will be non-zero if there's no beyond the standard model physics. And then there's, again, the A3 term, which is the coupling constant for CP violating couplings. So in practice, what we want to do is measure ratios of these coupling constants. That helps cancel out systematics, and then it gives us a nice fraction where we can measure some coupling constant relative to the pure standard model coupling constant. and it'll be nicely bound between 0 and 1. So you can see on the left, these are the 4 ratios we measure for the HVV vertex. And on the right, this is the 1 ratio we measure for the GG8 or the HGG vertex. And since any CP violation present in one of the vertices will affect the measurement in the other vertex, we keep them simultaneously unconstrained in the fit later on. So we just let them both float. So the nature of these couplings will actually affect the event kinematics, and that's how we can actually gain access to study these coupling constants. So what happens is, depending on the nature of the HVV or HGG vertex, the correlation between associated particles will change. So you can see on the bottom left, I've got this VBF Feynman diagram. And as I mentioned, there's these 2 quarks produced in association with the Higgs. And so based on the nature of the coupling, the correlation between these 2 quarks will be different. And then for the GGH production here, you can see there's no associated particles produced here. So in order to access the coupling, we need to have 2 additional jets radiated away during the Higgs production. And so the correlation in these jets ends up showing up in kinematic variables. So this is what's shown on the right-hand side. So on the top right, I've got the VBF production, and this is the azimuthal angle between the 2 associated jets. So you can see in black, this is for a pure CP even Higgs coupling, and in the red is the pure CP odd Higgs coupling. So clearly the shapes are different, but you should notice that they're both symmetric across 0. And then in green and blue, these are different mixtures of CP even and CP odd states. So you can see they're clearly different based on the nature of the mixture, but what you should notice that these couplings or these distributions are not symmetric about 0. And then if you look closely at the GGH production in the bottom right, all the signals are kind of mixed together, but if you look closely, you'll see the same trends where the pure states are symmetric about 0 and the mixed states are not symmetric. And there's clearly a difference between CP even and CP odd states here. So in addition to just using the kinematic variables, we can actually build dedicated discriminants to target different couplings. So that's what we'll do, and I'll discuss that later. Since we have to measure the correlation in these associated jets, we need a detector. So this work was done using the Cms Detector, which I've got a cutout shown on the top right, and then on the bottom right, I've got a cross section here with a couple particles showing how they propagate through the detector and how they're detected. So the main component of the CMS detector is a solenoid that produces a 3.8 Tesla magnetic field. That's what the S in CMS stands for. And so when an interaction happens in the detector, charged particles coming from that interaction point will be bent, their path will be bent by the magnetic field as they proceed through the tracker, which is the innermost layer of the detector. So the tracker is silicon pixels in layers. So as a particle leaves the detector, it interacts with different layers, and we can build up a track. And you can use the curvature in this track to measure the charge of the particle and the momentum of the particle. After leaving the tracker, a particle will interact with the calorimeters. So first the ecal, the electromagnetic calorimeter, which collects the energy from electromagnetically interacting particles. And then the hadronic calorimeter, which detects things like pions and neutrons. And so these calorimeters, they absorb all the energy of the particle, and then they give you a reading of the energy. And so if a particle makes it through the hadron calorimeter, these are usually muons that are able to do this. They'll pass through the solenoid, and into the muon chambers. And that's what this light blue line on the bottom right is. You see a muon passing through and going into the muon chambers. And so those report back, and we can match those to a track in the tracker. And so the way the whole system works is that all of these subsystems combine their information to identify particles, to identify what kind of particle you have. So for example, the electron here is shown in red. So what you can see is you've got a bent track inside the tracker, and then an energy deposition in the ecal. So these two systems communicate with each other. They combine information, and you can use the information from the two systems to identify that this is an electron. This is how all the particles are detected through different combinations of the subsystems. And then the neutrinos, they won't interact with the detector. So since we know this is happening in the center of mass frame, you can sum the momentum of all the objects in the event. And if you've got an imbalance in momentum, then you can assume that is the vector along that imbalance is where a neutrino carried away some of the energy. And so in this indirect way, we can measure the energy carried away by neutrinos. And so not included on that last diagram are the tau leptons. That's because the taus are heavy enough to decay inside the detector. So they decay weakly, meaning they can decay leptonically into electrons or muons and neutrinos, as is shown in the orange colored box at the top right. And they can also decay hadronically. So the hadronically decaying taus we identify using the hadron plus strips algorithm. And what that will do is it identifies the taus, and it describes them using different numbers of prongs. So a prong is a charged pion in this case. So you can have, as you can see at the top right in green, you can have a 1-prong or a 3-prong tau. And these also come with different numbers of neutral pions. So in this way, you can determine what kind of tau, or how the tau decayed using this hadron plus strips algorithm. And we should note that since in all of these decays there are neutrinos, you can never fully reconstruct tau lepton decay at CMS, because these neutrinos will carry away some of the tau's energy. So since the taus decay inside the detector, and we have to identify them based on their decay products, they can easily be faked by jets, electrons, or muons. So I've got two examples of this in the bottom left. This is how an electron can fake a hadronically decaying tau. So what you see is an electron radiates away a photon at the bottom left, and this gets identified as a neutral pion. And then the electron itself deposits some energy in the ecal and the hcal, and this gets identified as a fake charged pion. These two together end up giving you a 1-prong pi0 tau decay. Then on the right-hand side, this is how a jet would fake a hadronically decaying tau. So you can see all of these constituents inside this jet can be misidentified as charged pions or neutral pions. But the thing to see here is that in this jet of hadrons diagram, the particle multiplicity is much higher, and it's not nearly as collimated as this tau, the bottom diagram. So there are some distinct differences that we can use to identify true hadronically decaying taus from these fakes. So the way we do this is using the deep tau algorithm. So the deep tau algorithm is it's a deep neural network, and it uses all of the inputs to the hadrons plus tau, hadron plus strips algorithm, along with a lot of other detector variables, train this network to identify or classify hadronically decaying taus into 4 categories. So it gives you a probability that this tau that you fed in is actually an electron, a muon, a jet, or a tau. It gives you a probability of those four. And then you can build discriminants to veto electrons or muons or jets using ratios of these probabilities. So that's how we make sure that we're rejecting as many fake taus as we can. So then we can move on to the details of this analysis. So as I mentioned earlier, the background is primarily Z decaying to 2 taus, and there are also events where jets are faking taus. So we've got the deep tau algorithm, and it does a great job rejecting jets that fake taus, but that's still a significant background. And so what we want to do is we want to use data-driven methods to get reliable estimates of these two main backgrounds. And then there's a variety of other smaller backgrounds that we can model just using Monte Carlo simulation. And so the selection that we apply for this analysis is requiring either a single lepton trigger or a lepton tau cross trigger to fire. And then we place cuts on the tau passing isolation and anti-lepton discriminators. These are the 3 deep tau discriminators that I talked about before. So really trying to make sure you've got a true hadronically decaying tau. In addition, you want to have one isolated lepton, either a muon or electron, passing its own ID. And then since these 2 leptons are coming from a neutral Higgs, you want to make sure that the tau and whatever your light lepton is have opposite signs. And since the Higgs should be being produced near at rest, the light lepton and the tau should be nearly back to back. So we require them to have a large separation in eta phi space. Then just to reject any TT bar background we might have, we veto events with B jets, and we veto events with extra leptons. And then the last thing is to reduce the effect of the W plus jets background, we require that events have a low transverse mass between the missing energy and the light lepton. So first talking about the data-driven estimate of this zeta tau tau background. What we do here is we use the embedding technique, which, like I said, is a data-driven method. So it's got a few advantages. It gives us much higher statistics than we could simulate in Monte Carlo. It gives us a better description of things like jets and pileup in the event because these things are coming directly from data. And then again, since most of the event comes directly from data, there are fewer corrections and then fewer systematic uncertainties with respect to using Monte Carlo simulation. So the way this embedding technique works is you look at events in data and you select events where Z decays to 2 muons. Then what you do is you go into that event, you remove the muon system, the 2 muons from that event. You use that di-muon system to simulate a di-tau system with the same kinematics. And then you plug this di-tau system back into the data event. So now you've got a hybrid event with the zeta tau tau decay coming from Monte Carlo and the rest of the event coming directly from data. And so I've attached just the visible Higgs mass here on the left using Monte Carlo and on the right using the embedded technique. And so you can see basically we get much better agreement with the embedded technique. And it's hard to see because I've added a lot of channels together here, but the statistical uncertainty is much smaller using the embedded. So this is great. This gives us a great estimation of our zeta tau tau background. So that's our largest background. And then we also want to do a data-driven method to estimate the contribution from fake taus. And so we want to do this because fake taus are first difficult to simulate, and second, since we've got a really good deep tau algorithm and the misidentification rate is so low, you have to produce very large Monte Carlo samples to actually get a decent sized sample of events with a jet actually successfully faking a tau. So instead we use the data-driven method, which provides us much larger statistics. And just like the embedded samples, it gives us a better description because these things are coming straight from data. So A simple example of how you could do this would be just estimating QCD. This is one of the sources of fake taus, jets faking taus specifically, but not the only one. But we'll start here just as an example. So what you want to do is you'll separate your phase space into 4 regions, as I've shown in this table, where we've got this A region, which would be our signal region, where you've got isolated taus, and the tau and the light lepton have opposite signs. And then you've got this region here where on the right where you've got B and D, where you flip the tau isolation and now you've got anti-isolated taus. And then you've also got control regions on the bottom here in C and D, where instead of opposite sign events, you're measuring same sign events. And so because the QCD doesn't have real taus, these are all fake taus, there's no reason to assume that they should all be opposite sign between the fake tau and the muon. So you assume that the ratio of anti-isolated to isolated taus should be the same in opposite sign and same sign events. And so what you can do is you can measure the ratio of isolated to anti-isolated events in the same sign region. This is the C/D I've got shown on the right. And then you can use this ratio to scale events taken directly from the opposite sign anti-isolated region. And this should give you a prediction of your isolated opposite sign events. So the shape comes from B, the B region, and then the C/D region scales your normalization. And this gives you a good estimate of your fake taus in your signal region. So this is the simple example. And now the way it's actually done in this analysis is the fake factors, which I'll go back here. This C/D ratio is called a fake factor. So we measure this fake factor in QCD events, TT bar events, and WJet events separately. We construct control regions for each of those, and we measure the fake factor separately. And then when you go to construct your final estimate of your fake taus, you apply fake factors that are the weighted sum of the fake factors from each control region. So you take the ratio of the number of events coming from a certain background over the number of events from all backgrounds, and you use that to weight the fake factor from each control region. And so you can do this bend in the jet multiplicity and the visible mass, so that this takes into account any relations in different regions of phase space. And then lastly, you can apply corrections to account for any biases you introduce when you're defining these control regions. So in the end, what you get is an estimate of jets faking taus from QCD, TT bar, and W plus jet events. And so that's nice. Now we've got a data-driven estimate of our largest 2 backgrounds, zeta tau tau and jets faking taus. So to improve our sensitivity, what we do is we categorize events into 3 separate categories. First, we've got the 0 jet category. This is events where there are 0 jets present. So this has a very low amount of signal in it, but it's a very high statistics region. So when we do the fit, this really constrains our background normalization. On the other hand, we've got the VBF category here in the bottom right, where you've got 2 or more jets and high dijet mass. So this region is designed to target the kinematics of VBF production. And so something that we found was that actually the GGH events that were most interesting for this analysis were those that looked most similar to VBF events. So this VBF category is actually, in practice, it targets both gluon-gluon fusion and vector boson fusion production. So this is where we've got really good signal sensitivity. And then all the events that don't fall into either of these 2 categories fall into the boosted category, which has, it's got moderate sensitivity and moderate statistics. But you know, it would take a more dedicated approach to really get the best out of the boosted region. So now moving on to the observables we use in the analysis. First, just a note, these plots are all blinded with this blinding procedure shown in red at the top right. So if the signal over the square root of signal plus background is greater than 0.5, we don't show the data in that bin. And so the first observable I'm showing here is the dye-tau mass reconstruction. So the dye-tau mass for our signal samples should be the Higgs mass. And then this allows us to separate Higgs to tau-tau from Z to tau-tau because they should peak at different masses. So what we do is we use the fast MTT method to reconstruct the dye-tau mass, which this is just a common method used in Higgs to tau-tau. And what it does is it takes both of the tau4 vectors. So when I say tau here, I mean the leptonically decaying tau and the hadronically decaying tau. It takes both tau4 vectors along with the missing energy. And what it does is it calculates the most likely dye-tau mass after accounting for the energy that's carried off by the neutrinos. So the missing energy is used to do that. And it also calculates the most likely full tau for momenta. So that's including the neutrinos and the two taus. And so this, like I said, is great to separate any of our signal processes where a Higgs decays to two taus and the dye-tau mass should peak around the Higgs mass, from Z to tau-tau where the dye-tau mass should peak near the Z mass. As you can see in these bottom three plots, these are the dye-tau mass in our three different regions: zero jet on the left, boosted in the middle, VBF on the right. So in blue and red, you can see the dye-tau mass peaks around 125 for our signal samples. And then in the orangish yellow color, this is our embedded background. And this peaks near 90 GeV, as we expect for a Z. And then you can also see this is nice to reject some of the QCD background, which it doesn't have any dye-tau mass resonance. It's spread across the phase space. So you can see you can reject jet fake events that are far from the dye-tau mass, or far from the Higgs mass. In addition to the dye-tau mass, we make heavy use of the matrix element likelihood method. This is called MELA for short. And so what MELA does is you provide the 7 MELA input variables, which are shown here on the right, the top right. These 7 input variables completely describe the system in the dye-jet center of mass frame. And so using these 7 input variables, which have completely described the system, MELA determines the probability for different matrix elements. So it determines the probability that this event came from a process with this certain matrix element. For instance, gluon-gluon fusion, you can feed in events and get the probability that these events were produced from a gluon-gluon fusion process. And so using these probabilities of events coming from different processes, you can build dedicated discriminants. There are 3 general types of discriminants you can build, which I've shown on the bottom left here. So you can build first a discriminant against backgrounds, where you just use the probability of a standard model signal and the probability of your backgrounds, as you can see here in this ratio. And we don't use this discriminant in this analysis because in practice, we have multiple backgrounds and it's difficult to write a matrix element that accounts for all the backgrounds at play. So we decided to do something different for background discrimination. But then in the middle here, this is the beyond the standard model discriminant. So you can see this can separate your standard model production from a beyond the standard model production. This is shown in the middle plot here for VBF production. So you can see on the left-hand side in red, you can see the pure pseudoscalar Higgs production is shifted all the way to the left, peaking at 0, where the pure scalar Higgs production is peaking all the way on the right in black. And you can see these are symmetric again. Or these are not anti-symmetric, sorry. Not they're just not symmetric. But if you look at the blue and green, these mixtures are now symmetric, about 0.5. So what you can see here is this discriminant is optimally separating our CP even and CP odd states, pure CP even and CP odd states. And you can build discriminants of this type to separate your signal, different signal processes where you can write down the full matrix element. And then the last kind of discriminant we can build is this discriminant that's sensitive to the interference between standard model and beyond the standard model signals. So this is shown on the right, where again, we're looking at the VBF production. And you can see now in black and red, this is the pure CP even, pure CP odd states are symmetric about 0, and they look very similar to each other. But now you can see these mixed states where you've got interference between the two states look drastically different from each other, and they're not symmetric about 0, but you can see one of them peaking around -1 and one of them peaking at 1. So in this way, you can construct a discriminant that's sensitive to the interference terms as well. And so we make heavy use of the beyond the standard model and the interference discriminants. In particular, we build 3 discriminants for VBF and 3 for GGH. We start with just the general beyond the standard model discriminant, separating the standard model coupling from, for instance, a pseudoscalar coupling. This is shown for signals and background now on the bottom left here, where we're separating standard model VBF production from pseudoscalar VBF production. You can see in orange pseudoscalars peaking around 0, and in red scalars peaking around 1. We also build this D2 jet discriminant. This is useful for separating standard model VBF production from other signal productions, specifically separating standard model VBF from gluon-gluon fusion production. Since, as I mentioned, we allow the HGG and HVV vertices to float in the fit, it's useful for us to have a discriminant that actually separates the signal for HVV and the signal for HGG. So that's what this D2 jet discriminant's doing. You can see in the middle, VBF production's peaking around 0.3, while GGH production's peaking near 1. So this gives us good separation between these two signals. And last, as I already showed, we construct this mellow discriminant that's sensitive to interference. This is again shown on the right for VBF production. And again, we've got different shapes for a mixed state shown in pink here, and a pure CP even state shown in red. And so, as I mentioned, we don't use the Mella discriminant for backgrounds. Instead, what we do is we train a neural network discriminant to separate our signals and backgrounds. So what we start is we start by training just VBF versus zeta tau tau, because VBF is it's our more sensitive signal, and zeta tau tau is our largest background. So we train a network just to separate these two processes, and the output from this network is the probability that this event was a VBF event. And so we train this network using the 7 Mella input variables that go into Mella as well. And then we also include the di-tau mass, which I've got on the bottom right here, the visible Higgs PT, which is on the bottom left, and the di-jet mass, which is in the middle. So that's 10 input variables. And you can see clearly these 3 kinematic variables I have here have separation between the VBF production in red and the zeta tau tau production in kind of the orangish color. So the neural network we train is just a 2-layer densely connected network, 10 input variables. The first layer has 20 nodes, the second layer has 10 nodes. So this is shown on the right with all the connections here. In the hidden layers, we use the ReLU activation function, which is shown on the bottom left here. And then in the output layer, we use the sigmoid function because we use that in conjunction with the binary cross entropy loss function, which the sigmoid and its first derivative are shown in the bottom middle here. And then while we're training, we monitor the loss to make sure there's no overtraining occurring. So this is shown in the bottom right. So if you look at the top panel of the bottom right, you can see our training loss and our validation loss are converging simultaneously. So it doesn't look like there's any overtraining occurring here. So we're confident that this network should generalize well. And so we look at the neural network outputs. On the bottom left, that's for the mu tau channel, and on the bottom right, that's the e tau channel. And we start by seeing that, as expected, we've got good separation between VBF and zeta tau tau, with VBF peaking near 1 and zeta tau tau peaking at 0, just as we expect. The next thing we see is that this network actually does a good job separating gluon-gluon fusion from our backgrounds also. And then you combine that with the fact that the gluon-gluon fusion events we're most interested in are those that look like the vector boson fusion. So we feel like we don't need a separate network for gluon-gluon fusion. We can actually use this one network for both production modes. And then the last thing we see here is that actually all of our backgrounds are peaking near 0 and being well separated from signal. So the end result here is that we can train a network to separate just VBF versus zeta tau tau, so a very simple network. And it actually provides good separation between all of our signals and all of our backgrounds. So we can do everything we need to do with just this simple network. So then moving on to the results. The way we do this is we start by making a 2D distribution of the neural network discriminant and the MELA beyond the standard model discriminant. And so we do this separately for different bins of the D2 jet discriminant. So, you bin in D2 jet, and then you construct this 2D discriminant in each of those bins. That ends up giving you a 3D discriminant. So the Higgs combine tool that we use doesn't handle 3D discriminants. So what we want to do is we want to unroll the neural network and the beyond the standard model MELA discriminants into one dimension. So you can see here how this works, where looking at the top plot, you can see in blue, we've got different neural network bins. And then within each neural network bin, we've got the value of the MELA discriminant for picking out GGH. So you can see MELA discriminant for GGH in a certain neural network bin. And so what this does is it allows us to take this 2D distribution and squash it into one dimension. So now what we've got when we include the D2 jet discriminant is 3 variables packed into 2 dimensions that we can fit with the combine tool. So when we do this, these are the impacts. And so the main thing to see here is that I believe it's 16 of the top 20 impacts here are bin by bin statistical uncertainty. So what we're seeing here is that really this is statistically limited analysis, and we can improve just by improving our statistics. And then we end up doing the fit. We do it separately for the single electron, single muon data sets in 2016, 2017, and 2018. And then we also do combinations. So what I've got shown here is I've got all 3 years added together, and then I show in green the electron channel, in blue the muon channel, and in black the combined channel. So in black, that's all 3 years and both channels combined together. So what we do is we use the maximum likelihood method To infer these couplings, and like I said, we fit the two vertices individually, allowing the other one to float in the fit. And right now, only the expected results are shown. We're working on going through the unblinding procedure with CMS right now. So when we get the approval to unblind, then we can have some observed results. But what we see here is, as expected, the muon channel is more sensitive than the electron channel, and the HVV vertex is much more sensitive than the HGG vertex. So HVV is on the left, and HGG is on the right. So HVV is above 2 sigma for all the different combinations, where let's see, it looks like the muon channel barely gets above 1 sigma in HGG, and the combination gets a bit above 1 sigma. So these are the expected results, and hopefully we'll have observed results sometime soon. And then here, this is, again, the HVV vertex, but now this is the FA2 ratio, the F lambda 1 ratio, and the F lambda 1 Z gamma ratios. And you can see we've got good sensitivity in these as well, and hopefully we'll have observed results soon. Just the conclusion, I've presented the most sensitive analysis of the HVV production vertex in the Higgs to tau final state to date, and the first analysis of the HGG production vertex in the same Higgs to tau final state. So this e-tau and mu-tau channel are going to be combined to other tau decay channels, and then hopefully that will be published once we get everything unblinded.